So the error backpropagation algorithm, the algorithm to train a neural network, it can be summarized like this as some loop statement. The first what we do is we initialize all w values to very small numbers, and I said that the small numbers ranges from 0 to 1. And what we do is for each training example from the 1 to the n, we repeat all those things. And these two steps are forward steps. And these four lines are backward steps. Backward step. So for each training example, for the nth data points, what we do is we find the value of hj and ok by these formulas, which means that because we have these numbers and this number and this number, which is randomly chosen initial solution, initial value, so we just multiply the x value to those values and then make the summation and pass it through the sigmoid function. Then we can find the value of hj, which means that from h1 to hp, we can find the numbers of all those hidden, the outputs at hidden nodes. Because we found those values and then we have the randomly chosen values here, we can also find the numerical value of OK, which is quite at the very initial stage. This is quite a stupid value. That must be there must be a big difference between this predicted value and true value. Anyways, because we randomly chose that in W values, and then after that, once we find those values, once we've found those values, then we can evaluate this one, this quantity, the gradient information, using this formula that we found in the previous slides. Because this one is the true value at case output node, and this one is predicted value computed at the previous step, and this hj is also computed value at this stage. So we can numerically find this value, and also we can find numerically this value. Okay, so because we find this, because we found these two values, the current wkj can be updated by this formula. This point is what? This point is gradient descent method. So we can optimize, we can minimize the error function, and by this gradient descent method. So here is the current value, and here we have the current gradient information. Here we have learning rate, again, which is chosen by your choice, and then we find the new value of wkj, and then by this formula we can also update the current wji values. So this one is, again, this one is the weights between what? Hidden layer and output layer, and this one is the weights between input layer and hidden layer. And then because we have updated value, we repeat this whole procedure for the next one, for the next data points. Then we can get the updated value of this one, and we can repeat the whole procedure for the training examples. Okay, then the question can be arising like this. So we already used up from D1 to Dn for this for loop. Then what if this condition is not satisfied even though we used up all those examples? Then start from D1 again. And this kind of update rule is called online learning. So we update the weights value in the neural network by passing one data points at once. Okay, that is called online learning. And another way to train a neural network is something called batch learning. Then in this case, uh, actually we do not learn about this case, but in this case, what you do is, in fact, from this whole slide we find these things. We find the partial derivative of E sub n wji and round E sub n over round w, what is that, the kj. Instead of evaluating these two, what you can do is we can directly find this one and wkj. So here this E is the summation over from I1 to I equals to 1 to n, and capital N, the number of observations, not here, n, the index must be n. The summation of En, right? In fact, we can find those things. Then this formula can be redefined, and it must be different from this one. That case is called batch learning. It means that we pass the whole data points, all of the data points through the neural network, and then we repeat again for the whole data points when we update these W values. Let me explain in Korean again. 그러니까 이거는 데이터 포인트 하나하나를 뉴럴 네트워크 이제 이렇게 인풋 레이어, 히든 레이어, 아웃풋 레이어 있으면 여기 W들 이제 업데이트 하는 거잖아요. 처음엔 그냥 랜덤으로 딱 정해놓고 데이터 포인트 하나 통과시켜서 그 에러 보고 요거 업데이트 하는데, 그 다음에 또 두 번째 업데이트 할 때는 현재 업데이트된 W에 기반해서 두 번째 데이터 포인트 이렇게 쭉 흘려보내면서 또 업데이트하고 이런 식으로 하는 거잖아요. 데이터 포인트 하나씩. 왜냐하면 우리는 요거를 계산해서 업데이트 하니까요. 그런데 아예 이 에러 펑션, 그러니까 데이터 전체에 대해서 더한 얘를 이 WJI에 대해서 편미분하고 WKJ에 대해서 편미분하면 그 식이 좀 달라져요. 이게 서메이션 I 인덱스가 들어가는 형태로 나와요. 뭐 정확하게 그냥 딱 서메이션으로 떨어지진 않지만, 그래서 그런 경우는 이게 뭐냐면 그냥 우리 데이터셋에 n개 데이터 포인트가 있으면 이거를 그냥 전체 다 보내고 걔네 이 모든 에러를 다 줄이는 방향으로 한 번 업데이트하는 거예요. 그리고 또 전체 데이터를 쭉 흘려보내서 또 업데이트하고, 이런 경우를 우리가 배치 러닝이라고 불러요. 그러면 이제 우리 요거를 이제 다시 유도할 필요가 있는데, 그거는 이 수업 시간에서는 다루지 않았습니다. 근데 뭐 굉장히 유사해요. 유사하고 수식도 사실은 굉장히 유사하게 떨어집니다. 그래서 뭐 굳이 다룰 필요는 없고, 그래서 두 가지 러닝 방법이 있다는 거, 온라인 러닝과 배치 러닝. 그 다음에 한국말로 한 김에 우리 그냥 교환학생들에게는 미안하지만 이 에러 백 프로퍼게이션 알고리즘을, 그러니까 여기서 에러가 정의되고 그 에러를 이용을 해서 우리 W를 업데이트하는 거잖아요. 이 백워드 방향으로. 그래서 여기 에러를 미니마이즈하는 요거 업데이트하고, 혹자는 이렇게 얘기하는 분이 있기는 해요. 이거 잘못된 설명인데, 여기서의 에러를 미니마이즈하는 W를 업데이트하고 이렇게 표현하는 분이 있어요. 그래서 이 이거 인풋, 만약에 히든 아웃풋, 이렇게 레이어가 뭐 만약에 5개가 있다고 합시다. 그러면 여기서 에러를 미니마이즈하는 여기 업데이트하고, 여기서 에러 미니마이즈 하는 여기 W 업데이트하고, 이게 아니라 여기 에러를 미니마이즈하는 여기 업데이트하고, 여기 에러를 미니마이즈하는 여기 업데이트하고, 여기 에러를 미니마이즈하는 여기 업데이트, 여기 에러를 미니마이즈하는 여기 업데이트예요. 그러니까 우리가 여기서 W들을 다 업데이트 할 때, 우리 아까 여기서는 요 WKJ 할 때는 식이, WKJ, 케이스 1 할 때는 식이 좀 상당히 간단했어요. 이렇게. 그 1차 미분 정보가, 그레디언트 정보가. 그런데 여기 업데이트 할 때는 어때요? 좀 복잡하죠? 그리고 여기 서메이션 이렇게 있고, 텀이 훨씬 많습니다. 그래서 그 이유가 뭐냐면 우리 그냥 미분 제가 이제 그 미분의 의미로 이해를 했는데 여기 W 조금 변할 때 여기 에러가 얼마나 변하느냐 요거를 이벨루에이션 한 거잖아요. 그래서 이게 히든 레이어가 많아지면 많아질수록 어떻게 돼요? 어떻게 되냐면 우리가 곱해야 되는 이 미분 정보들이 훨씬 더 많아집니다. 근데 게다가 다 미분 값이에요. 그래서 이 히든 노드가 많아지면 많아질수록 이 W를 이벨리에이션 하기가 이 에러를 미니마이즈 하는 이쪽에서의 에러를 미니마이즈 하는 이쪽 W를 찾기가 업데이트하기가 점점 어려워집니다. 이런 거를 우리가 그레디언트 베니싱 베니싱 프로블럼이라고 불러요. 스펠링이 맞을 거예요. 베니시 사라지는 거. 그러니까 이런 걸 이제 그레디언트 베니싱 프로블럼이라고 하고 이제 딥 뉴럴넷의 굉장히 큰 문제 중에 하나인데 어, 이 그레디언트 베니싱 프로블럼이란 걸 만약에 이제 들어본 적이 있는 분은 여기 이제 우리 웨이트 업데이트 할 때 이렇게 그레디언트 정보가 많이 곱해지니까 이 히든 레이어가 많아지면 많아질수록 업데이트하기가 어렵겠구나. 그냥 이렇게 이해하시면 됩니다. 그래서 이거를 뭐 해결하는 방법은 또 뭐 여러 가지가 있어요. 여러 가지가 있는데 그런 거는 뭐 지금이 이제 딥 뉴럴넷을 가르쳐 주는 시간은 아니니까 그냥 참고로 좀 말씀을 드립니다. 한국말로 얘기한 김에 얘기했고. Okay, so we talked about the difference between online learning and batch learning. So that is so all this procedure is called error backpropagation algorithm. So if you understand this algorithm, then you can notice why the name of algorithm is called this one, error backpropagation algorithm. Okay, we backpropagate the error defined at the output layer. Okay, then here is a example XOR problem that we took a look at at the very beginning of this slide. So to solve this problem, what we actually make is this structure. There are two input nodes and there are two hidden nodes. In fact, you can make another one, 3 nodes, 4 nodes, 5 hidden nodes. That they are okay. But in this case, we just use 2 hidden nodes and there is one output node because here we have only one no, only one, not only one. Here we have 2 classes. So this value can take either 0 or 1. So in fact, instead of this one, you can make like this: x1 and x2 and h1, h2, and then o1 and o2 by o1 and o2, so that this for the class 1 can be encoded into I'm sorry, class 0 can be encoded into 1 0 for O1 and O2, and class 1 can be encoded like 0 0 1. Okay, you can transform this value to this case, this value to this case if you want to use this structure. So this structure is also fine. But in this example, we use only one output node, okay? And then we want to find from W1 to W9 from these 4 data points, okay? And at iteration 0, what we do is we just randomly pick up numbers. So all these numbers are initial solution, okay? So you can see that the output of neural network seems quite stupid, right? So using the error backpropagation algorithm, we update these values by the gradient descent method. Then this one is the updated value after 10,000 repetitions. Okay. Then still the output of neural network still seems stupid. So we repeat again and again. This is the updated W values after 2000 iterations. Then still not good, but after 3000 iterations, the output of neural network seems better than before, right? For the class 0, the output value is 0.3, and I'm sorry. And for the class 1, the output value is greater than 0.5. It seems that, and then for the last one, the output of neural network is 0.11. So it seems that by using these values, I think we can classify these four data points correctly. After 5,000 iterations, it seems better. It seems much better. And after 10,000 iteration, the output value is quite close to these true values, right? The difference between true value and predicted value is very small. So if we repeat, and repeat that weight updating procedure again and again, then we're gonna get very close, how to say, the values that are very close to true values, which means that quite a smart neural network that can return the values that is close to the values that are very close to the true values. Okay, then this graph shows as the iterations go forward, we can see that the error becomes smaller and then close to zero. Okay, this slide shows that. And here is an R example. In fact, there is a package in R software where we can use the neural network, and this is a classification problem. Here, this is a map of Italy, and this is a north and central and southern part, and then the olive oils produced in different areas, they have different characters. Actually, that is this problem starts from that. So in olive oil data set, we have this number of observation. There are 3 classes and 8 independent variables. I don't know about all those things. It seems that they are the chemistry terms, but I don't know about it. So you can download that olive data set from click this link, then there is a link to download that data set. And that data set looks like, where is it? This one. So there are 8 x variables, and I think this one is response. No. This column. Reason is the class variable. 1, 2, 3. And I think 1 indicates the north, and 2 is central, and 3 is the southern area. So this one is a class variable, and these are the independent x variables. And let me just copy all those. This is just to split into training and test set by stratified random partitioning. So let me just copy all those things, and then run the codes line by line. This line is to read Olive dataset into R session, and then what you do is, because the reason column has the values of 1, 2, and 3, I'm gonna change that as that column as a vector type, and then for the first to 11th column, what I'm gonna do is, using this scale function, I'm gonna standardize that x variables. So I forgot to mention that in neural network, if we want to use neural network, all those x values must be normalized or standardized. Okay, so you cannot use the original scale. So please normalize, which means that all those x values fall into the range from 0 to 1, or it make like each column has mean 0 and the standard deviation 1, the standardized step. We have to do that. We have to go through that procedure. So this line is to make a standardized data set. So let me just evaluate this part. This one is the original data set, and once we standardize I'm not sure if I explained about this scale function before, but that is by setting center equal to true and scale equal to true, it means that we standardize the data set. So just like this. Okay, they are the standardized values. And then change those columns using this standardized data set. And then to perform this stratified random partitioning, what you do is, I'm gonna delete the first and third column because they are not used for this classification task. And this one, the area and the row names, and then this one is, I guess, the name of a city. So we're gonna delete those two columns. After that, let us take a look at the first few lines of this one. Head d.olive. Okay, so here the first column is class variable. We make subsets for each of the classes. We split into 3 data sets using these 3 lines, and then we randomly shuffle the rows of each of the data sets. So this one is just to figure out the number of rows for each of the data set. And let me check, the class 1 observation is 323, and the number of observations for class 2 is 98, and the number of observations for the class 3, the southern part, is 151 observations. And then using this sample function, randomly shuffle the rows for each of the data sets and make partitions into training and test. So as you can see from here, the first 70% will be used for training on neural network, and the remaining 30% is the test set. Okay, and then using this rbind function, merge those training for each of the classes, and then using rbind function, merge all those 3 data sets into one test set. Okay, then we have d.olive.train and d.olive.test. After that, what you're going to do is we have to encode the class variable into 3 columns using this class.ind function, but that function is in fact implemented in nnet function. So you first to attach this nnet package into your R session library using library command nnet. If you don't have this package, you can install using this install button. Okay, then you can use this class.ind function, and the input argument of this function is the class values that is in a factor type, right? Then using this function, what you can do is it is encoded in this way. The value of 1 becomes 100, and 2 becomes 010, and 3 becomes 001. Okay, and that is named as nny.train. For the training set, for the test set, we do the same thing, and using this cbind function, and we exclude the first column. What you're gonna have is this one. So the x values are the same as before, but the class column becomes 3 columns indicating each of the classes. Okay, we do the same thing for the test set. We have to make our training set in this way to use a neural network and to use this nnet package, nnet function in this nnet package, neural network, for training on neural network. After that, only this line is to train a neural network. So the input of this nnet function is that matrix or data frame for the x variables, and then matrix or data frame of the y values, and here the size is the number of hidden nodes. So to know more about this nnet function, you can use help function. Then here you can see the input arguments here. You can specify x and y. Also, you can specify as a formula. And then here the size is the number of units in the hidden layer. And this nnet function is an implementation of the neural network having only one hidden layer. So we cannot specify the number of hidden layers. So this is just case of one hidden layer. Okay, and here max IT is the maximum number of iterations, maximum number of repetitions. Okay, once we specify it like this, then after 100 iterations, it stops the updating the weights. Okay, here the this nf function is in fact the implementation of batch learning. This is not a sequential learning, online learning. This is batch learning. So using this just one line of command, we can train a neural network. Okay, and this is initial value of what? Error function. And error is now decreasing as iteration goes forward. Okay, so after 100 iterations, it stops training the neural network, and that result is stored in this R object. Okay, then the next code is to find training error and test error. Because this is a classification task, we're gonna construct 2 confusion matrices for training and test respectively. So here this pred y is the predicted value of the neural network is stored in this R object, which name is fitted value. Okay, let me just evaluate this part. Then these are the outputs for each of the observations. So this one is the output at the first output node, this one is the second output node, and this output is the output of the third output node. Then what you're gonna do is we use apply function. We apply this function row-wise, right? What is the which.max function does? What this function does? It returns the index of the maximum value, right? So if we run this code, then it returns the index of the maximum value, as you can see from here. So that is the predicted class, right? And then this one is in fact encoded into this way, encoded in this way. So if we apply the which.max function, then for the first row it returns 1, and for this row it returns 2 because this 1 is the maximum value. So using the same way, we're gonna get the true class value like this, and then using the table function we can make a confusion matrix like this, and the training error is, as you can see from here, training error is 0. Okay, there is no misclassified observations for training set, so which is quite accurate. And for the test set, so let us compute the training error. So this part, this one returns true or false. If the predicted value and true value they are different, it returns true, and if they are the same, it returns false. And using summation function, we can count the number of observations that are misclassified, which is 1. Okay, there's only 1. Okay, there's 1 observation that are misclassified. I would say one class 3 observation that is predicted as a class 1. Okay, so the training error is this one, 0.00249 something. This one is training error. And we do the same thing for the test set. What we're gonna do is we use predict function, and its first argument is trained neural network, and we put that trained neural network the test set, and then the type is low, which means that the low predicted value will be returned by this formula. Okay, can you see that? And then we also apply, we also use this apply function. We apply which.max function to return the predicted class. This one is the predicted class, and this one is true class, and here we have a confusion matrix for the test set. And for the test set, the performance is also very good. Only one observation is misclassified, so the test error is very close to 0. So we can almost correctly classify this OLIVE data set using neural network. Okay, and I already explained about this thing. This shows the steps of iterations, and we can see, because the numbers are different from what I showed just before using R software, is because we started from different weights. Okay, so it's different, but you know, after, I think this case even the iteration doesn't reach to the 100, I think. And this is okay. In this case, actually, both training and test error is 0. And this is the this slide shows the neural network that we just used. We set we have 8 input variables, and we have 3 hidden nodes and 3 output nodes because there are 3 classes, and this one indicates the bias terms, so the constants adding to each of the hidden node, and then this one is the bias, the constant term adding to each of the output node. And actually, in fact, once we train a neural network using nnet function, in fact that returns quite many outputs. What is the name of trained neural network? This one, nnet n dot olive. Then there are many outputs in it, and we use this one fitted values to find the true class value. And here the what is that, the WTS, this one is the optimal solution, that the weights in the trained neural network. And then if you use the summary function and that olive, then it shows in more detail about the weights. So here from B to H1 is the constant at H1, that is 7.24, which is this value, and this value is the weight between the first input node and then first hidden node. Okay, and then this one is the weight between second input node and first hidden node, third input node and first hidden node. So all these indicates shows all these they show the weights going into the first hidden node, and the next line shows the weights going into the second hidden node, third hidden node, and this one is the weight between the first hidden node and first output node, second hidden node and second output node, third hidden node and third output node. Oh, I'm sorry. Forget about what I just explained. So this one is the weights going through the first output node. This is the weights going into the second output node and third output node. Okay, and this is in fact a numeric vector, but you can easily mapping those values. Here this value is this one, this value is this one, this value is this one, and this value is 25.25 is this one, and 2.71 is this one, the next bias term. Okay, so you can easily mapping all those numbers with this one. So the reason that I explained about this output and this one is because once we train a neural network, then by storing these numbers only, we can make predictions. So this is a way of saving a neural network with a very small size of information. Okay, it's just piece of information, and this function is to just to observe the decreasing error by learning. Let me just learn this thing by learn the code, and I want to explain about this one. Okay, so in fact this nnet function can receive another input argument which is WTS, so we can explicitly define the initial weight value. If we do not specify this value, this nnet function randomly choose the initial W value. But if we specify that initial weight value, then it starts from this initial value to solve that optimization problem. Okay, the training neural network. So in this way, what you do is we set that initial weights as a zero, just zero. So we start from 0 point in 39 dimensional. Okay, because there's one more dimension which is error function. We start from origin in 40 dimensional space, and then we're gonna find the direction, the gradient information at that in that 40 dimensional space, and we move along with the negative gradient direction, and then reach to the optimal point, which is the ideally zero error. But we may not be able to reach to that 0 point, but that is our hope. We want to reach to that optimal solution. And this max epoch is maximum number of iterations. Okay, so here's one more information for you. In online learning, another name of online learning is sequential learning. In that case, each repetition is called iteration. But for the batch learning, each repetition is called epoch. It's just a convention used in this society. So the maximum number of epoch, maximum number of repetitions in batch learning is set to 100, and then this err.vic is to store the error value at each of the epochs. Okay, so we repeat the training neural network using nnet function from 1 to 100. So in the case of I equals to 1, is that it's just one epoch. Okay, it's just the result of the one epoch. In the case of I equals to 100, is that the trained neural network is the result after 100 times repetitions. Do you understand that? So because we specify max iteration as I. Okay, so when I is 1, it's just the output. This nn dot olive is the trained neural network after one iteration, one epoch. And if I is 50, that result is the trained neural network after 50 epochs. Okay, and then this one nn dot olive at a fitted value is predicted value, and this one is true value, and that is stored as a em, and em times em is a matrix element-wise multiplication, and this is the squared error, and this we sum all those squared error to calculate error. Okay, and we repeat all those things. Okay, there's no max epoch, and then we repeat all those things. And then by plotting that error, oops, okay, we can observe that error has been being decreased. Okay, we can see that. So that's why we specify here the initial weights to get the same not the same neural network. The neural network started from the same initial points. That's why I specify here the initial weights. Okay, so one more tip for you is I'm spending much more time than I expected, but I want to give you more information. So here, nn dot leaf our object has the trained weight value here, right? Then what happens if you train the same data set with the specification of nn dot leaf at weights with the same structure of the neural network, then it just finishes quickly because we started from very good initial solution. Okay, do you understand that? Please, I hope you please get the sense of a training neural network. It is in fact solving a nonlinear optimization problem. So if we start from very good initial solution within very small number of within very small number of repetitions, within very small number of iterations, we can get a quite good neural network. Okay, and then this is a regression example, and I told you that in fact the neural network can be used for regression problem, and this part will be explained in the next video clip. I want to stop here. And in fact, I wanted to finish everything about the neural network for this class, but let me begin from this slide in the next class. Thank you for your attention.